inter-integrated circuit here. Okay, this particular circuit is a inter-integrated circuit which you are going to have. So inter-integrated circuit. So this particular device. So their I2C square um, circuit bus. Okay, so this particular bus will be used to connect two different devices. What are the two different devices it is going to cover? Connect is the next question. So it is going to make the synchronous bidirectional of duplex communication. So that is, it is going to communicate one at a time. That's it. Okay. So it can communicate either from the source, from master to slave, or from slave to master. From the figure we can see that. So it's going to have two different types of lines. One is your serial control, serial clock line, serial clock. So that is SCL stand for, here you can see it is a serial clock. So your SCL stand for serial clock. So whereas your SDA stand for serial data. Okay, our SCL stand for serial data. Now, when you are going to have serial data, so this particular SCL line which is there, so SCL line is mainly responsible for generating the synchronizing system, synchronizing clock pulse. Okay, so if you take the synchronizing SCL synchronizing clock, so it is going to make use of to generate the synchronization pulses. Okay, so what do you mean by synchronization pulse is the next question. So it will generate the synchronization pulse which you are going to have. Okay, so synchronization pulse is, so to whom you have to make a communication, to have the communication with any of the devices, okay, which you are going to have. So I have to establish the connection between that particular device. Okay, so next is SDA. So you can take that it is SDA. So here this is SDA. So SDA is basically used to transfer the data. Okay, so it is going to be used for transmitting the serial data across the devices. So it is basically used to transmit the data along the device. Okay, so transmit the data along device. So along this device. Okay, so now if you take the IT is a shared bus either, so it is going to have two different types. So one is the master, other is slave. So you can see it here. This will be your master. The microprocessor which you are going to see, this will be your master. The devices which are connected to that particular master are slave. Okay, the devices which it is connected to that particular master is the slave which you are going to have. So this is your microprocessor will become a master device, whereas your slave will become the slave device. So to move the master, so now who is going to initiate the communication is the next question. So your master device is responsible for controlling the communication. Okay, so your master device which is there here, the master device is either it may be a microprocessor or microcontroller. So that is the main, so which will be used for controlling the communication. So the master device is responsible for communicating the communication. Okay, so it is responsible. So it is going to have the responsible for communicating. It is responsible for communicating with the devices. Okay, so it is going to have the response for communicating and initialization. So but who has to initiate it? So because if I want to transfer data, if I want to transfer the data to the slave device, whether I have to terminate the connection or whether I have to establish the communication, so that has to be done, right? So who has to that particular initiation? So that particular initiation will be done by your master device. Okay, so the master device is responsible for controlling the communication. By how it is going to communicate, it is responsible for communication by initiating or transferring. Okay, by initiating or terminating. So initiating is nothing but starting or terminating the session. So your master is mainly responsible for initiating and transmitting the necessary. So now, depending upon the type of the communication which you are going to have, the master has to send the clock pulses, depending upon that one, or when I have to shoot. So before I start sending the communication, I have to inform to the other person, that to the slave, that I am going to make the communication. So if you are receiving the data from some other line, so don't use that particular line. It is not only that the only master is communicated to that particular device, slave device. Okay, so there may be a number of master device, it may be communicated in your embedded system. Okay, so at that time what will happen? So it will first, it has to initiate the connection, and it has to send the data which is necessary for synchronization of the pulses. Now, so once the master has done that one, okay, master has done this one. Now what is the work of the slave. Okay, so the now what is the work of the slave we are going to have? So the work of the slave is the what? So the work of the slave is to wait for the commands from the master. So the work of the slave now is become what? Wait for the commands from the master. So it is going to wait for the commands which will be coming from the master. It will wait for the commands from master. Okay. So now when it is receiving the commands from the master, okay. So when it is receiving the commands from the master, so and upon receiving the command, what it has to do? So either it has to uh, serve the request which is requested by the master processor or slave processor. So if we take the master slave, so if we take the master slave device, so if we take either it may be a master or slave. So always you take that your master will be your master is will be your microprocessor or microcontroller. You can see it here. So this will be your master. That is your microprocessor. Okay. So the microprocessor always will be the master. So now when you take the master or slave, both devices, either master devices or slave devices, so can act as either transmitter as receiver. Can either be acting as can act can either be transmitter or receiver. So it is going to have the master device can be working both as the master as the device. So regardless if the master is acting as a transmitter or receiver, so the synchronization clock signal is generated by the master device. So whether your master is going to be transmitting or receiving, whether your slave is going to receive the acting as a transmitter or receiver. So regardless of which one is acting as a transmitter or receiver, so the synchronization clock pulse is to be generated by the master only. Okay, so that means what? So you have to make a note here that always the synchronization pulse has to be done or generated by whom? Which device? Always the synchronization pulse has to be always the synchronization pulse has to be generated by which device? Master or slave? Has to be generated by
Master.
yeah. Always it has to be master only. So only the master has to be initiating this one. So now if we take the I2 square, that is integrated circuit, so it is going to be support multi-bus architecture on the same bus, multi-bus master on the same bus. So it is going to make a note that so it is going to have the multi-masters. Okay. So it supports multi-master. What it tells, it supports multi-master means what? I can connect another microprocessor. Okay, so I can connect another microprocessor for this two bus. Okay, you're going to have two different bus, that is I2 square, I2C bus. One is your SCL bus, other is SDL bus. Okay, so that is serial clock bus and a serial data bus, which you are going to have. So okay, so when you are going to have the multi-master, so it is going to support multi-master. That is for this particular SCL, SA, SDA, multiple masters can be connected. So another master I can connect here for this bus, same bus. Okay, so another master, multiple master I can connect. Okay, so your I2 square bus is built around an input buffer. Okay, so it is going to be built on open drain or collector transistor. So basically, if your bus you are going to have, the bus is going to be built by the transistor. So the whatever the bus you are going to have, that is built using transistor. So that will be built using transistor, which you are going to have. Okay, so for that particular reason only, you should know the working of the transistor every time. So you can so now when you complete your embedded system, you come to know that what are the applications you have studied in your ADE. So almost all the ADE applications you are going to implement here. So that's what we are telling frequently, that you have to study the ADE perfectly. So so when the initiating is going to start is the next question, right? So whenever you are going to have this particular thing, so when the initiating is going to start is the next question. So initiating is going to start when, okay, so just 1 minute. So, okay. So now when this particular initiation is going to start is the next question. So if we take this particular part, so initiation is going to happen when the initiation is going to occur. So if there is the initiation, with respect to this particular bus and master. So when the bus is in idle state, so if any, if we take either it is SCL or SDA, so these two are bus. Okay, so now consider when this is in idle state, because when you can make the communication when there is no communication is happening between any of the devices. When we are telling that multi-master can be um, connected to that particular I2 square bus, what will happen? So other master can be communicating with the slave device, right? There is a possibility. There is a possibility that other master device can be communicating with that one. So now, what will happen at that time? So when the bus is in idle state, so whenever the master wants to communicate with the slave, what will happen? So the transistor which will be there, so the output, the transistor which will be there, that will be turned into a high impedance state. So here, when it is idle state, when initiation has to occur. So when initiation has to occur, so when initiation takes place, what has to be done? So if initiation has to take place, so first what it has to do, first it has to, whatever the output lines you are going to have, so the output lines where you are going to make the communication, output lines has to turn to high impedance state. Okay, so I has to switch to high impedance state. The output lines has to switch to high impedance state. So this has to be turned into switch into the high impedance state. Okay, so that is what it is going to happen. So now proper operation of the bus, what will happen? Both the bus line should be put to the supply voltage plus 5 volts. Okay, what I tell that. So when you are going to have this particular, if they are built using the transistor, so assume that it has been built using the transistor. So if the transistor is built means what? If these two lines has to work, that is STA, you have to give voltage, right, to that particular line. So the minimum voltage what you have to give is plus 5 volts. Okay, the minimum voltage what you are supposed to give is plus 5 volts to make your to make your bus to make active. So which will make you inside that one, you can see that two resistors are there here. So you are going to give the VCC of plus 5 volts here. So VCC is there right here. So that VCC for plus 5 volts you are going to give. So with the help of the VCC, what we are going to give for plus volts, so it is going to reduce to 3.3 volts. Okay, so this particular voltage is going to reduce here by 3.3. Why? So because of this particular resistor, you have the register here is there. So whatever the register you are going to have there, that is going to pull down the register to around 2.2. Okay, so it will reduce from to reduce the voltage, and whatever the register it is going to be connected, so that will be acting as a pull-up resistor. So the output lines of the bus will change in the idle state, now will become high. So whenever the voltage you are going to give, so what will happen? So the bus state will go to high state. The bus state now will go to high state. So initially it will be the idle state. After giving the voltage, the bus state will change to high state. The bus state will change to high state, change to high state after providing the voltage. Okay, after giving voltage. Okay, after giving voltage you are going to have. Okay, so now once you have given the voltage here, so the sequence of operation has to be done. So that now whenever you want to make the communication either with the master or to the slave or slave to the master, so it is normal. But yeah, so if you want to make a communication with any one of the person, what you should have, first you should have the address line, right? So if you want to make a communication, the communication will be done with respect to address. Okay, if you take any communication, so even if you want to write a letter to some friend, so that address should be there. Even if you are writing a mail through your email, so the address will be there, right? So that particular destination recipient address which should be there, that should be there. So even if they here also, if the communication has to be done, so what has to be there? The address should be there. The address should be there. So now whatever the address is there, so it is hardware. So whatever the address you are going to have, it is hardware. So that means what? So it is going to have the electronic circuitry. It is inbuilt. It is going to have the electronic circuitry, and that particular circuitry is inbuilt. So electronic circuitry and is inbuilt. So that word it is called as hardwired. Hardwired means what? So that is inbuilt circuitry it is going to have. Hardware represent through inbuilt circuitry. So inbuilt circuitry it is going to have. So that is what the meaning of the hardware. Okay. So now when it is going to be having hardware, so here you can see it here. See, it is going to follow the some sequence of operations for communicating within. So IIC slave devices. So the, to slave devices, it has to perform some operations. Okay, what are the sequence of operations it will be performing? Let us see that one. Okay, so when it is performing this particular operation, so some set of sequence of operation it has to perform. So what it has to do first, the first operation, what it has to do is, so here, so first the faster measure pulls the clock line of the bus to high. As I told you that the voltage will be given, right? So the voltage, why it is given? To pull the bus to high. Pull bus to high is the first work what you need to do. So because if you are, want to transmit a data from either from slave to master or from master to slave, I have to give the voltage, right? So who has to pull the voltage? First, the it is must that the initiation has to take it from the master only. So first it has to pull the bus to high. By whom? By master. By whom it has to be done? By master it has to be done. Now, once you have done, so when you are when your device pulls the loan to high, what will happen? So even at that time, since you are not using the data line, since I am establishing the communication, to establish the communication, first I am using the serial clock pulse. So now your serial clock will be going to high. Okay, your SCL is going to high here. Bus to high means what? SCL is going high. So next, simultaneously, both cannot be high. Both your SCL and SDA cannot be high. So your pull SDA to low. Second is pull SDA to low pulse. Okay. So this will be high pulse. This will be low pulse. So third is now the master device sends the address of the slave device. Next, to whom it has to communicate. So the master has to communicate to the slave device. So the slave device will be having some one address. So now to whom the master has to communicate. So that particular master device has to send the address. So master sends the address. Okay, master sends the address. So the address will be in the range of 0 to 7 bits to 10 bits wide. So the address will be from 0 to 10 bits wide, 7 bits to 10 bits wide. That means what? At most you can have 2 power 7 to 2 power slave devices can be connected. So that in place that you can connect 2 power 7 to 2 power 10 slave devices can be connected here. Okay, can be connected. Okay, so that what it comes to. So now the master device sends the address to the slave device in which it wants to communicate over the STI line. So the address will be sent through the address will be sent through the SDA line. So what through where I have to send the data. So now after establishing the connection, the clock pulses are generated at the SCL line for synchronizing the bit reception by the slave devices. Because next I have to do the synchronization, right? Synchronization means what? So both the master to whom it is communicating and the slave which is receiving, both has to be synchronized, because when I'm throwing something means the slave has to receive in the proper way. For that particular reason, both has to be synchronized, your master as well as the slave. Okay, for that particular thing, the data in the bus is valid through the high period of the clock signal. So once the establishment of the clock is done, so the clock pulses generates synchronization signal. So here the clock pulse generates synchronization signal. Okay, so once the synchronization is done, so it has to be ready to terminate transfer. Now, once the synchronization pulse is ready, so what I can do, so now everything is ready. The master is ready to send the data or read the data, read or write the data. Either slave device is ready to read or write the data. So now the master device, what it has to do now the master device, once the synchronization is done, so the master device sends the read or write bit. That means what? So it is either at the receiving end or transmitting end. So if it is at the transmitting end, it will write there, it will place the bit onto the bus. Okay, that is which bus it is going to place. It is going to place on the SDA bus. It is going to place on the SDA bus. So now, normally what will happen whenever the read or write bit sends the read or write bit. So what it indicates that, so if it is that particular read or write bit, that will be having first, I should know that what operation I am going to perform, whether I am going to perform the read operation or whether I have to perform the write operation. So now, if that particular bit is 1, if read write bit is 1, then it is going to perform read operation. If bit is equal to 1, that is going to perform read operation. If bit is 0, that is going to perform write operation. If bit is 0, that is going to perform the write operation. So next, after that one, once the master device is once the master device sends the waits for the acknowledgement bit from the slave device whose address is sent on the bus along with the read write operation command. Okay. So next, what it has to do. So now I have told that this is the address to whom I have to communicate. Now, next, whether the slave is busy or free, idle, I don't know. So for that one, what the slave has to send? The slave has to send the acknowledge, telling that I am free, you can send the data. Okay. So now fifth step is what? The master waits for the acknowledgement. So your master waits for acknowledgement. Okay. So it will wait for the acknowledgement. Okay. So it will wait for acknowledgement and it is going to establish and it is going to initiate the either the depending upon the bit what it is going to receive. So if the bit is 1, it is a read operation. If bit is 0, then it is going to have the write operation. So depending upon that that one, so the slave device connected to the bus compares the address received with the address assigned to them. Okay. So after the acknowledgement comes, the slave device, whatever the address the sent by the master, it has to tell that the whatever the address is assigned to me is proper. So I am the one person who is going to communicate with the master. So that it has to be referred like the referred. Okay. So next, the master after sending that one, so the slave device with the address request by the master device responds by sending the acknowledgement bit. Okay. Now after the master waits for acknowledgement, so who has to send the acknowledgement? Slave will send the acknowledgement. Slave will be sending the acknowledgement. So acknowledgement bit it is going to send acknowledgement. So that will be 1. It is going to send over the STA line. So this particular acknowledgement bit is going to be sent through the STA line. So now once it is done, upon receiving the acknowledgement bit by the master, so again the master will send what? Data. If it is at the transmitting end. So if it is at the transmitting end, the master sends data of 8-bit. So the master sends data of 8-bit over the SDA line to the slave device over SDA line. Okay. So if the requested operation is write to device over the SDA line, if the requested operation is write to device. Okay. So if the requested operation is read from the device, the slave device sends data to the master over the SDA line. Okay. So if it is from master to slave, the master has to write the data on the SDA line. So if the data is transferring from slave to master, the slave has to write the data onto the SDA line so that it has to communicate to the master. So once the data has been transferred already, so your 8th. So the 8th step, what it is going to do. So your master waits for the acknowledgement bit from the device upon by transfer complete. Okay. So your master device, what it is going to have, the master device waits for acknowledgement. So you're going to have the master device. So it waits for acknowledgement. Wait for acknowledgement. Okay. So for what acknowledgement it is going to wait? So whether the transfer is completed or not. Acknowledge stating whether the transfer is completed or not. Whether the transfer is completed or not. Okay. So that's what is going to happen there. So next exercise, the master device terminates the transfer by pulling the SDA line high again. So after that one, so I have to terminate the connection. So who has to initiate again? Again, the master device has to initiate the connection. So here again, the master device terminates the connection. Terminates the transfer of data. Okay, transfer by pulling SDA line high. Okay, by pulling SDA line high, so it is going to transfer. So now, if they place the clock 6 line SL to a logic high, So what it now it is going to indicate that, so it is going to be a stop condition. So that is whatever the data I have to send to the either to the from slave to master or from master to slave. So that particular process is completed. Then I have to terminate this particular connection. So this is how your I2C square will work. So this is important for your examination point of view. Okay. So because most of the time in your final exam, in your embedded system itself is a separate subject. In that particular subject, they are going to ask that one. Okay. So this is important. So the next one will be your SPI bus. Okay. The SPI bus is the next one. So SPI bus is a bidirectional full duplex 4-wire serial bus. Okay. So if you talk about the SPI bus, so all of you are able to see the presentation, or still there's a whiteboard only.
PPT is visible, sir.
PPT are you able to see? Presentation are you able to see?
Yes. Yes, sir.
Okay. So now, so next is your serial peripheral interface bus. So it is a bidirectional bus. Okay. So it's a bidirectional full duplex bus, which is having the 4-wire serial interface. Okay. So it's going to have the 4-wire serial interface, and it's a bidirectional because both the slave and master can transfer and receive the data simultaneously. To full duplex means what? So the data transfer is going to happen to and fro at the simultaneously from transmitting into the receiving end. So this particular bus is first introduced by Motorola. So whereas your I2 square bus is first introduced by your Philips semiconductor. So this serial bus, the peripheral interface bus, is the first introduced by Motorola. So here, so whereas in your I2C, it is multi-master, multi-slave. But whereas in your serial peripheral interface, it is a single master, multi-slave. That's one difference you have to keep in your mind. So your SPI is a single master, multi-slave system. Whereas your I2C is a multi-master, multi-slave, because I can have multiple master connected across the bus. Okay. So SPI gives 4 signal lines for communication. What are those signal lines? The 4 signal lines for communication which they are going to give is, one is master out, slave in. So that stands for signal lines carrying the data from masters to slave device. Okay. So that is one line which is used for signal lines to carry the data from the master to the slave device. That is master out, slave in. That is master out means what? Who is sending the data? Master is sending the data. Okay. So slave in must mean what? The slave is receiving the data. So next is master in, slave out. So now master in means what? You are receiving, you are at the receiving end. So that means signal lines, this particular communication line will carry the data from signal lines carrying the data from slave to master device. Okay. So next is serial clock. So it's going to have the 4 communication line. Third is serial clock. So this particular line is going to communicate with respect to serial signal line carrying the clock pulses. Okay. So serial clock, it is going to be signal lines carrying a clock pulses. Next is self select. So signal file for particular slave device select. Okay. Since we don't have the multiple device transfer, so it's only single master, multiple bus. So now slave select line or signal line, what it is going to do? So it is going to signal line for slave device select. So that particular, you are using that particular slave select line, you are going to select a particular slave. Okay. So it is at, normally it will be at active low. So normally it will be at the active low. So now here also the same thing, similar to our I2 square. Who has to initiate the communication? Who will be initiating the communication? If we take your I2C, who will be initiating the communication? Whether it's a master or a slave. In your I2C, who was initiating the communication? Either master or slave.
Master.
Yeah. So here also, the master is responsible for generating the clock pulse. So he has to initiate the communication. Okay. So now, so how it is going to select is the next line. So you can see it here. So by generating the clock pulse, that is by generating the clock pulse, it has to initiate the connection. So when you are going to have the device, the master device is going to generate the clock signal here. So when it is generating the clock signal, so how it has to be, so what it requires, it selects the required slave devices. You can see it here, SS1V and SS2V in the figure. So these are the thing which you are going to have slave select 1 and slave select 2. For this particular master, so two slaves are connected. So by using any of the select line, that is any of the slave select line, I have to select that particular slave. Now, once you know that one, so your master, what it is going to do? So master selects the required slave device. Okay, how it is going to select that one? So it is going to select by select signal low. So you're going to have the select signal. So that is slave select signal, right? So so if you want to select this particular device one, it will send low signal to the SS1V. That is, if I send this particular low signal to SS1V, that is slave select one, then it is going to select slave one. So if I am sending low signal to SS2, then it is going to select slave 2. Okay. So depending upon the low signal, how the master will send, that particular slave will be selected here. So if you want to select slave 1, it will make your SS1 line to low. If I want to select slave 2, it will make SS2 line to low. So when you are going to have this particular line, whichever the line is low, that particular slave will be selected. Okay. So now, whenever a serial data transmission is going to happen, so that has to be done in fully configurable. Okay. So it's going to contains a certain set of registers for holding these configurations. Okay. So it's going to have some set of registers inside your processor, so which will make you to hold the configurations. So what are the different parameters it has to do? Because when you talk about the communication, the communication normally it will be normally with the communication rate will be represented by baud. Okay, so how much baud you are going to have. So whatever the baud rate you are going to have, so that is going to be making use of baud rate. Okay, so some baud rate will be there. Depending upon that particular baud rate, it is going to communicate. So here the SP serial peripheral control register, which will holding the configuration parameters like master slave selection for the device, baud rate selection for communication, what is my clock signal, and who is going to transfer. So and the status of who is transferring the data from master to slave. Either the transfer of data is going from master slave, or communication is coming from master slave to master. This information will be stored in that particular register. Okay, so basically it is going to hold your SPI, that is serial peripheral interface bus, is normally works with the principle of shift registers. So okay, so what we have studied in your ADA class. So it is going to have the separate shift register for the data to transmit or receive. So that is out of this your knowledge how it is been done inside that one. So the size of the shift registers which you are going to have to transfer the data, it depends upon the type of the it depends upon the size of the shift registers which you are going to have. So normally whatever the shift registers you are going to have in your SPI, so it will be in the power of 8. Okay, it will be in the power of 8. So it is going to have, so when compared to I2C here, so SPI bus is more suitable for application requiring transfer of data in streams, because it's going to have the by a fully bidirectional duplex communication. Since it is having the fully duplex communication, normally, so the master device here, as I told already that, so your master device is responsible for generating the clock signal. So same thing I have here it is mentioned. So it is going to contain the shift register. The size of the shift register is divided independent. So normally what is the size of the shift registers? It will be in the multiple of 8. So whenever the transmission is taking from master to slave. So now when the data is coming from master to slave, the data in the master shift register shifted out to the MOSI pin. So MOSI pin is nothing but what? So it is master out, slave in pin. Okay. So the data in the master shift register, whatever the data is there in the master shift register, it will be shifted out to the MOSI pin, because your MOSI pin is going to send the data to the slave. So here in the MOSI pin, if the master is at the writing end and if the slave is in the reading end, that is master out, serial in pin, and it enters the shift register of the slave device through the MOSI pin of the slave device. Okay, so both your MOSI pin will be there connected. MOSI pin will be connected both to your master as well as the slave. Okay. So now MOSI pin shifted out from MOSI pin, and it will enter the shift register of the slave device through the MOSI pin only, because your slave device will be at the receiving end at that time. Okay. So at the same time, the shift out data bit from the slave device shift register enter the shift register of the master device through MISO pin. Okay. So since it is a bidirectional transfer, both master and slave can communicate simultaneously. Okay, can communicate simultaneously. So your shifted out bit is from the slave device shift register. So it has to send to the master now. So now the master will be at the input end. Your slave is at the output end. So now where the slave has to place its data, the slave has to place the data in MISO pin. So when it enters the shift register of the master device through MISO pin, what it indicates? It indicates that the data will be sent by the slave and the master is going to receive that one. So now in summary, the shift registers of master and slave devices form a circular buffer. Okay. So that means nothing but what? Circular buffer is nothing but what? It's going to send the data from master to slave, slave to master again from master to slave, and it is going to be slave to master. So it will be in circle only. So it is going to form the circular buffer. Okay. So that's what your SPI stands for. So next, when it comes to the application, of your SPI, so normally it is going to be used in data in streams where the data is continuously flowing. Because when you talk about the shift registers, which can send that data in the form of streams, so it is going to have the data in terms of 8-bit. So the only limitation it does not support is an acknowledgement mechanism, because whether the communication is happening properly or not, we won't come to know as of in I2C. So whereas in I2C, what was happening, the acknowledgement has to come from the slave before establishing the connection or before the data is sent. So that is going to happen in your SPI. Okay. So that is about your SPI. So anybody having any doubt in I2C and SPI? So if we take the difference between I2C and SPI, so these are some of the differences. So what are the speed limit varies from 100 kbps, 400 kbps, 1 mbps, 3.4 mbps, depending on I2C version. So more than 1 mbps, 10 mbps, still 100 mbps can be achieved in SPI. That is, the data rate will be more in SPI. So in your I2C, it is off duplex synchronous protocol, whereas your SPI is a full duplex synchronous protocol. So whereas your I2C supports multi-master configuration, whereas your SPI supports multi-master configuration is not possible. Okay. Acknowledgement of e-transfer is there in I2C. No acknowledgement is there. So it is going to have I2 is going to have 2 lines, which is SD and SCL, whereas in your SPI is having 4 lines. That is master in serial out, master out serial in, clock and slave select. That's chip select signal for each slave. So addition of new device on the bus is easy. Okay. So since it is having only 2 lines, so addition of new device on the bus is not much easy as I2 because you are going to have 4 lines and only one master can be connected to each device, and you have a limitation that how much slave can be connected to that particular master. So if it is having the limitation of having only one slave can be connected to that particular device, then you cannot connect more than one device to that particular device. So that is one overhead. So more overhead is there due to the acknowledgement start and stop it. That is overhead means what? The data transmission will take more time because we have to receive the acknowledgement. After receiving the acknowledgement, I have to check that whether the again I have to check that whether the line is idle or not. If the line is idle, then only I have to send the data. So if the line is not idle, I cannot send the data. So it is going to have the less overhead. So since it is going to have only one master connected to that particular line. So if more masters are connected, I don't know that who is initiating the connection simultaneously. Because if you are connecting with only one master, so then the communication will become easy. So if the communication is easy means what? So you're going to have the less overhead. That's it. So noise sensitivity is high. So where there is more amount of transmission is happening inside your I2 key. So whereas your less noise sensitivity will be there. Okay. In your I2 SPI. Okay. So this will be about your onboard communication. So other 3 are there, which is another one is important, which is request universal asynchronous receiver transmitter. Okay, so that we will cover the future classes. So anybody having any doubt in this from this class? Anybody having any doubt? So anybody having any doubt? If you have any doubt, you can